waiting for the time, you know.
Okay, I think we are live. So, hello everyone, and welcome to the Latin American webinars on physics, law of physics. Today we'll have the webinar number 196, and it's our pleasure to have today Sreemanti Chakraborti. So, Sreemanti did her PhD in IIT Guwahati in India, and then she had a postdoc appointment in LAPTH in Nancy. And now she has a second postdoc appointment at IPPP Durham. And today, Sreemanti will talk about quantum sensors and ALPs, insight and open question. So it's a pleasure to have you here, Sreemanti. So I think you can start sharing your screen.
Okay, so thank you, Nicolás, for the invitation, and it's a genuine pleasure to be able to talk about my work on a platform like law physics. So the topic of my talk today is something I've been exploring over the last couple of years since I joined Durham as a postdoc, and this is also mostly based on one of our recent works that came out sometime last year. So today, I want to share a bit of that perspective, that how I see the field evolving and what kind of questions we are working on now in precision phenomenology and quantum sensing, and where I think the next meaningful steps might be. So I'll keep the focus on axion-like particles and ultralight dark matter, and I'll touch on both the theory and the experimental side. Especially the opportunities that quantum technology are opening up. So let me begin with a very broad view that we have extremely compelling gravitational evidence that something non-luminous makes up about a quarter of the universe. And this shows up in rotation curves, gravitational lensing, the CMB, and the large-scale structure of the cosmos. So what we do know is essentially the macroscopic behavior that dark matter is abundant, pressureless, long-lived, and effectively charged neutral. However, what we don't know is what really matters for particle physics, which is it a fundamental particle? If so, then was its mass or its spin, or does it have any non-gravitational interactions that we can actually probe? And also, about its production in the early universe, that was it produced thermally or through some other non-thermal mechanism. So all these unknowns translate into a very broad range of possibilities for the mass of the dark matter particle. So this is one way to visualize that range, that dark matter particles span many orders of magnitude in mass from ultralight bosonic dark matter fields down at 10 to the minus 22 electron volt, which we called ultralight fuzzy dark matter regime, to all the way up to composite objects and even primordial black holes. And then somewhere in the middle of the range, we have our more familiar WIMPs along the electroweak scale, which up to the unitarity limit. So this mass range is extremely broad, and different parts of these possibilities of the mass range motivate very different experimental approaches that we have come across over the last couple of decades. So for a very long time, most of the experimental effort focused on thermal WIMPs, or weakly interacting massive particles. So what the basic idea is very simple, that if dark matter interacts with standard model particles at roughly the weak scale, then we can look for it in three complementary ways: in direct detections, by measuring nuclear recoils underground. Also, we can find dark matter in collider production, like at the LHC. And lastly, in indirect searches, where we can look for the annihilations or decay products of dark matter interactions in the form of gamma rays or cosmic rays in the sky. So these complementary approaches formed a very robust program for many, many years, but the direct detection bounds have now pushed deep into the parameter space. So this traditional WIM focus picture is quite constrained at the moment, and that has naturally encouraged us, which is the community, to explore other mass scales and other kinds of interactions. So once we look below the traditional WIM scale, we naturally open up a whole range of possibilities for lighter dark sectors. So for example, in the MEV to GeV mass range, the possible search strategies look quite different. Instead of nuclear recoils or missing energy at the colliders, these models are often probed through beam jump experiments or through the rare decays of light mesons, or even scattering of electrons or lighter nuclei. So the phenomenology is much richer, and the experimental landscape is very, very diverse in this mass regime. And this region has seen a huge amount of activity in the last decade. So between accelerator-based experiments, fixed target setups, and rare decay searches, we now have a very dense set of constraints along across the MEV to the multi-GeV range. And as I said, it's a very active part of the BSM parameter space, and which still continues to grow. So this naturally leads us to consider further alternatives, especially in the very low mass regime. So one of the most interesting alternatives to look at dark matter that is much, much lighter is where the behavior is no longer particle-like at all. So what really happens when dark matter is this light? So now we're talking about dark matter masses below one electron volt mass scale. So what happens is, as we move down to very small masses like this, two things essentially happen. First, the de Broglie wavelength associated with these fields become astrophysically large on the scale of kiloparsecs. And secondly, for a fixed energy density, the number density grows. So as a consequence, many particles pile up into the same state, giving us a very huge occupation number. And this is why ultralight dark matter in this mass range can't behave like individual particles anymore. It effectively becomes a classical wave with its dynamics governed by the classical wave equation, which is what I'm showing here. So once we treat it as a classical wave, we can describe it simply as a coherently oscillating bosonic field with its amplitude fixed by the local dark matter energy density, which is the expression we can see here. Also, the angular frequency is essentially set by the rest mass of the particle, and there are also small corrections from kinetic energy suppressed by the relative velocity square in the halo, which is about one part in a million, as we can see here. And then lastly, the finite velocity dispersion here also gives the field a finite coherence time, which is roughly 1 million oscillation periods. So, and this long coherence time in the last line is extremely favorable for testing ultralight dark matter fields with precision experiments, which we'll see later, because it gives you a very clean characteristic signal when we try to probe it in the precision sensors. So that's the behavior of these classical fields today. Now, to understand where this field actually comes from, we can go back to the early universe. So in the early universe, the light bosonic field obeys this simple equation of motion, as we can see here. So then when the Hubble rate is much larger than the mass of the field, so the system essentially works as an overdamped oscillator. So that means even if we disturb it from its potential minimum, it would just stay frozen there and wouldn't move. But the oscillations essentially started when the Hubble parameter drops below the mass of the field, and so where roughly we can have this equality, and the field slowly started to roll towards the minimum of its potential. And as the universe continued to expand and Hubble became smaller and smaller than the mass, the field enters its oscillatory regime. And in that regime, the energy density scales as 1/a cube, just like ordinary cold dark matter or dust. So that's the standard misalignment mechanism, which is also shown here in the plot, where the oscillation starts and where the onset starts and all that, depending on the mass of the field. So now, so as I said, that the dark matter in this mass regime is essentially bosonic, but also there we have a lot of choice. So dark matter can be scalars, pseudoscalars, vectors, etc. So among them, a well-motivated example is the QCD axions. So just to give an example, to give a brief introduction, that axions were originally introduced as a solution to the strong CP problem through the Pechiquin mechanism. So their mass is set by the QCD physics and the PQ scale. So the interaction with the standard model that we can see here is essentially tied to the interaction scale. So the mass. So they have a very specific relation of the mass of those axion fields with its interaction strength with the standard model. And also they are essentially pseudo-number Goldstone bosons, which essentially implies a shift symmetry leading to derivative couplings of this structure. And lastly, depending on the parameters of the axion field, they can make up a fraction or even all of the dark matter in the universe. So here I'm just showing some very standard axion relation with for example, the effective Lagrangian, the mass to the decay constant relation, and the familiar the familiar axion photon coupling, depending on the choice of the QCD axion models that you choose. But then on the other hand, the ALPs, or the Axion-like particles, which are very similar, but they have an essential difference with the QCD axions that I introduced before, that ALPs don't solve the strong CP problem. So we don't really care about solving the strong CP problem here. So and then unlike and that essentially means that unlike the QCD axion, their mass is not tied to QCD dynamics anymore. So for ALPs, the mass is essentially of a free parameter. So which in that sense, ALPs are really a phenomenological construct, which is a very flexible proxy for light pseudo-number Goldstone bosons in a wide range of models. And lastly, they can still behave like axions, in the sense that they can still have derivative couplings and also can constitute a component or all of the cold dark matter density in the halo. Now, once we treat ALPs as a general phenomenological framework, so the natural question is how their interactions look across different energy scales. So what really matters for us is are these effective couplings. At the UV scale, we can write general operators with ALPs, which so in our work, so in this work, we'll be calling ALPs with this variable small a from now on. So at the UV, then we can write general operators involving quarks, gluons, and gauge bosons. So that's basically what is shown in this top box. So now through RG running and threshold matching down to the QCD scale, these interactions necessarily evolve and mix. So this is something we studied in detail in our paper last year. So which is to follow how these couplings flow from the high scales down to the hadronic scales. So which is important for us to probe these models with quantum sensors. So what happens is at low energies we match onto the chiral Lagrangian, where the ALP dependence appears here inside the quark mass matrix, so you can see here. And that dependence shows up if we start from the gluon couplings at the UV. So once you switch gluon couplings on at the UV, you will necessarily end up here with this, where you will have the quark mass matrix having a specific relation with your axion-like particle fields. So which is the expression we can see here. So now, once we match these UV couplings onto the low energy theory, something really important happens, which is, as we can see here, that the quark mass matrix has a specific relation with due to chiral rotation starting due to the gluonic interaction at the UV scale. So what happens is this pion mass gets an ALP field dependent correction, which we can see here, and which is proportional to the quadratic interactions of this in this ALP field. So you can see here that the pion mass gets a quadratic correction, which is proportional to the square of the gluon coupling and also the quadratic strength of the fields. And then and then through the chiral Lagrangian, these pion mass corrections feed naturally into the nucleon mass corrections as well. So as a result, we can have ALP-dependent shifts in the nucleon mass as well, as we can see here. So what really happens here is, so the key point is that so these interactions, which are quadratic in the ALP field, which are spin independent in that sense, which are scalar-like, and unlike the dimension 5 pseudoscalar couplings we can also get from ALP EFT. This is a bit different because these quadratic interactions are dimension 6. They are scalar-like interactions, and they are not optional. So they are not also model-dependent artifacts. So they are inevitable consequence of matching a UV gluon coupling down to the hadronic scale. So what we are left with in the end are all these shifts in pion mass, nucleon mass, and also these corrections automatically feed into the photon and the electron mass shifts, as we'll see later. So all these, so the important part here is all these interactions are dimension 6 spin independent in nature. So as I said, that the quadratic couplings don't just sit there in pion and nucleon mass. So they translate directly into the shifts of the fundamental constant through photon and the electron couplings, as we'll see here. So what really happens, just to make the point here, that through pion exchange and higher order loops, we can get quadratic couplings of ALPs with photons, as we can see here, and then also through a two-loop process, as we show in the bottom panel, one can get ALP couplings with the electrons as a form of four Fermi interactions. So as a result, this essentially gives us a quadratic ALP-dependent shift in the electron mass. So what's more important than the exact form of these couplings is the idea that by switching on just one coupling at the UV, we can automatically generate all these scalar-like couplings at the low energy. So now, as I said, that so once we generate these quadratic interactions with our ALP fields, they just don't sit there. They translate directly into the shifts of the fundamental constants. So here's the real payoff for the quadratic Lagrangian, that in the oscillating dark matter background, these quadratic operators translate into time-dependent shifts in the fundamental constants, like fine structure constant, as we can see here, which really comes from terms like this. And also we have quadratic shifts in nucleon mass and electron mass. So basically, these are the building blocks of atoms. So the fundamental, instead of the exact form of these interactions, what's more important that due to this, due to everything happening in the oscillatory ALP background, the fundamental constants of nature, like the fine structure constant, electron mass, etc., so these become dynamical in nature. So they oscillate in time at a fixed frequency, which is set by the underlying dark matter field, with a specific coherence time and with a specific amplitude, which scales with the energy density and the mass of the fields. So which is really the important takeaway from all this exercise. So now the question is, so this sort of oscillatory signals, as I said earlier, is exactly the kind of signals the high precision quantum sensors like atomic clocks, interferometer, resonators, etc. So they're exquisitely sensitive to. So now the question is, we have fundamental constants oscillating, but how do we actually detect that small oscillations? So now coming to atomic clocks, so if we ask that what's inside an atomic clock, so at the core of an atomic clock there are three main components. One is the atomic reference, which is a very precise transition between two energy levels of an atom. And secondly, we have an oscillator, which is usually in optical clocks a laser, or in microwave clocks a generic microwave source, so which is tuned as closely as possible to that reference transition. And thirdly, we have a very tight feedback loop that constantly compares that oscillator frequency to the atomic reference frequency. So which is very important to correct any drift in the frequency of the atomic clocks. So that tight feedback network is what helps atomic clocks to be so precise in timekeeping, because any small shift from the specified reference frequency will just show up in an atomic clock, because the feedback loop is constantly going back and forth between the oscillator and the atomic transition frequency. So then how does this feature help us to detect dark matter particles? So what really happens here, that this feedback network is highly sensitive to detect any shift. So this shift, if there is ultralight dark matter in the background, what we'll see is a very specific oscillatory shift, and that, if within the sensitivity of these atomic clocks, if it falls within the sensitivity range, then it will show up as a signal. So there are some subtle points here which will come later. So in a way, the prediction is a very distinctive experimental signal, that the shift itself is oscillating with a coherence time and at a very specific frequency. So now let me connect this to what clocks actually measures and how it connects with our fundamental constants that we saw in the first section of the talk. So what we compare here, so what we do actually to obtain a signal is to compare two different atomic clocks. So what we really look at is the ratio between the two transition frequencies. And that ratio can always be written in terms of the fundamental constants with some sensitivity coefficients, as we can see here. Also, all these kappa values. So these are the sensitivity coefficients sensitive to a specific atomic transition. So as we already see that these are essentially dependent on the fundamental constants, because that's what an atomic transition frequency is made of. So the only requirement to see a signal in is that the two clocks have very different sensitivity coefficients on these fundamental constants. Because if we compare two transition frequencies having the same sensitivity coefficients in the fundamental constant, then they will exactly cancel out when we actually look at the ratio. So the reason behind looking at the ratio is to cancel out the common noise. For example, so if there is a background shift due to temperature in the clocks, so comparing these two signals will immediately cancel it out because it's a common environment. But common environment should not also wash out the common signal. So that's the idea of having different sensitivity coefficients when we compare two clocks A and B. And then once we have this parameterization of different sensitivity coefficients depending on fundamental constants, it becomes very easy to plug in the shifts induced by the ultralight dark matter, as we see there, because this is the observable in the clock comparison test, which is the differential ratio of the frequencies of the two clocks we are measuring, and they are functions of the shifts of the fundamental constant times the sensitivity coefficients, which are measured using the experiments. So then the idea is that since this is a quadratic interaction and all these shifts in the fundamental constants scale quadratically with the field itself, instead of seeing a signal at the Compton mass, we here. So if there are ultralight dark matter signal, that would immediately pick up at twice the Compton frequency, which is a characteristic signal for this quadratic interactions playing in the background. So so before moving to real searches, let me just show the types of clocks people have actually used in precision sensing, because their stability is what determines how well they can see these oscillations. So we have broadly two classes of clocks. One is microwave clocks like cesium and rubidium, so which operate at gigahertz frequencies. And so they integrate for a long time, and they typically reach fractional uncertainties about 10 to the minus 15. And then we have the optical clocks, which are much more stable, which operates as hundreds of terahertz frequencies. So like clocks like ytterbium, strontium, etc. And so they are stable because their frequency, so the stability scales directly as the frequency and also the line width. So higher the frequency, the narrower is the transition and better is the stability, which is why the optical clocks are the most precise clocks as we have at the moment. So now let me very briefly compare clocks to optical cavities, which is essentially the same sort of system setup, but working on very similar principles. But comparing clocks with the cavities can give us a completely different handle on the same physics. So what are cavities? So cavities are essentially a system of mirrors with a laser shining between them, where the laser goes back and forth between the two mirrors. And instead of measuring atomic transition frequency. So what people really measured, so the cavity frequency is essentially the function of its length. So we actually measure the physical length. So the physical length variation is actually what makes a frequency variation for optical cavities. So the length in turn is proportional to the bore radius. So roughly, so the length of an optical cavity solid, which scales as 1/4 bore radius, and then the frequency of the optical cavities then scales directly with the fine structure constant and the electron mass. So what really happens now is when we compare an optical clock with an optical cavity, we can immediately isolate the fine structure constant, and which essentially gives us a signal, can give us a signal in this clock cavity comparison if there is a ultralight dark matter in the background. So cavities really can give us an ultrasensitive, but purely optomechanical probe, which is complementary to the atomic transitions that we see for the optical clocks. So now let me put all these comparisons together and show you what region of parameter space they can actually probe. So this plot shows the combined low frequency coverage from all the clock and the clock cavity comparisons. So each line, as we can see here, is corresponds to a different pair of systems, and each pair probes a slightly different combinations of the fundamental constants. And we show this in our in a CGG over F, which is the gluon coupling that we switched on at the UV in our Lagrangian as a function of our ALP mass. So we show all these clock comparisons in red and this clock cavity comparisons in blue. As we can see here, that the rubidium cesium microwave fountains push into the very small mass range, which is around 10 to the minus 21 and below. So it's essentially limited by how long you can run the comparison test. And then optical clocks like ytterbium strontium, as we can see here, which is really good for higher frequencies, or other optical clocks probe higher masses because of their higher operating frequencies and better stability. And then also we have the mixed systems here, like a hydrogen maser compared against a silicon cavity, which is essentially the comparison between hyperfine frequencies and optical frequencies, which have very different dependencies on the fundamental constant, and which makes the comparison even more interesting for looking for ultralight signals. So taken together, these systems cover complementary regions, and what's remarkable is that they can already probe deep into the interesting QCD-motivated parameter space, even though none of these experiments were originally designed for dark matter searches. So now let me very quickly put all these comparisons, also tell you that quickly go over to other experiments which nearly operates with the same principle, like gravitational wave detectors, like LIGO, etc. So which means that the clock systems, clocks and cavities are not the only place where the oscillations show up. So anything that depends on the fundamental constant shifts can in principle detect them. So one obvious system, as I said, are these gravitational wave detectors repurposed as laser interferometers. So what really happens here is very briefly. So this is a modified Michelson's interferometer which is a 2-arm laser interferometer, which basically measures the tiny differences in the optical path lengths between the two orthogonal arms. So even if the mirrors and the beam splitter are freely suspended, and even if we start from very roughly equal arm lengths. So there can still be tiny variations in the optical path length difference between the two arms. And then this, and also in these setups, this beam splitter also has a intrinsic geometrical asymmetry. So which really boosts the signal if there is an ultralight dark matter lagging in the background. So what really happens here is the optical path length, if there is an ultralight dark matter in the background. So instead of altering the space-time like gravitational wave does, so the basic principle is the same as gravitational wave detection. So instead of altering space-time, here we have an oscillatory background which is moving everything. So in a way that the optical path length difference, which is the observable, also oscillates, having the same properties. And then the interferometer becomes a detector for these fundamentally constant variations. So now, importantly, the gravitational wave detectors like LIGO are just very large and very stable laser interferometers, which operates around a few kilohertz. And they, as I said, can also be used or repurposed to measure ultralight dark matter in the range of 10 to the minus 14 to 10 to the minus 11. And also there are older gravitational wave interferometers like Q600, which operates at a slightly lower frequency, which if we convert it into the viable ALP mass range, comes to be about 10 to the minus 11 to 10 to the minus 13. So now, what really, another such system, what really plays is these mechanical resonators, so which is very similar to the interferometers, but in a way that these are more mechanical versions of the same idea. So these resonant mass detectors. So some of these have been used before in gravitational wave searches. So these are just solid objects whose size oscillates when the underlying constant shifts, either because of this, either because of a gravitational wave passing through or an oscillating dark matter passing through. Doesn't matter, but it's the same operating principle in general. And then if one of their acoustic modes lines up with the ALP Compton frequency, so that response can be resonantly enhanced. So one such example is Auriga, as we can see here. So Auriga is a classic example of this, which is a cryogenic resonant mass detector of a few meters length. So the idea is when the dark matter oscillates, so the fundamental constant shifts, so the atomic equilibrium spacing changes, and the length of the bar oscillates very slightly. But if this drives one of the bar's fundamental acoustic modes, then the resonance can be sharply amplified within a very narrow resonant frequency window. So and then it can be read out by a squid-based readout, and so this is sensitive to strains at the level of 10 to the minus 21, which is even better than the clocks, but within a very narrow range. So this gives a very narrow band signal, as we'll see later when we'll overlay all these constraints together. So in a way, this is an incredibly complementary part of the parameter space around 10 to the minus 12 electron volt, which we'll see in this plot when we overlay when we put everything together. So this figure again, we show it in our paper, and then we've shown everything in the gluon coupling over the ALP parameter space. So this summarizes all the constraints that can come from the low coverage, which I've already zoomed in for clocks and the clock cavity comparisons. So now we can see that at the higher frequencies where bounds from LIGO and Geo600, all those repurposed laser interferometers sit. And here we have Auriga, which I said is a very narrowband frequency, but has a fantastic frequency sensitivity, as we see here. So what's important is that this combined picture shows very clearly how we can have different quantum sensors carving out complementary windows around an enormous mass range. So we can see here that we've gone from fuzzy dark matter regime up to like very high masses of covering tens of orders of magnitude. And also, which is important, that no single experiment covers a whole range, because they all have their own limitations of their operations. But together, when we combine sensitivities of clocks, cavities, interferometers, and resonators, we can turn the precision sensing or precision metrology into a genuine dark matter discovery tool. So now we can I can go very briefly over the upcoming advancements that people are talking about. One is nuclear clocks, which is arguably the most anticipated advance in precision sensing. So what really happens here is in most atomic transitions which sit at electron volt to keV energy scales, this is the transition in thorium to 229 is exceptionally different from them because we have a near cancellation from Coulomb energy and nuclear binding energy, which gives a very special isomeric state lying at a few electron volts. So which makes it really easy to probe it using lasers. And also the boost in the sensitivity coefficients are huge because of that, because by definition the sensitivity coefficients physically signify the tiny change in the measurements compared to the states we start from. So here we can see that we can have a huge boost in the sensitivity coefficients, which really pushes the sensitivity of this nuclear clocks by large orders of magnitude from the current atomic clocks that we have at the moment. And then ultimately there's another alternative, which are atom interferometers. So where we have atomic wave packets split and recombined using laser pulses, and what we measure at the end of the day is the relative phase between the two parts of the split atom. And then we can so in atom interferometers, which is now under construction in the UK and in the US in two different experiments. So a very important handle in atom interferometer based searches is this baseline length, where we have gradiometers, which is a system of two or more atom interferometers separated by a distance. So which is basically taking the idea of atom interferometry one step further, that instead of one, we can just run two interferometers together, and which makes it very easy to cancel out the common laser noise and isolate the only dark matter induced phase in the signal. So, and since the sensitivity scales directly with the baseline length, which is the distance between the two atom interferometers, So, which is why we have the upcoming longer baseline proposals, and even a system of atom interferometers, or a system of old atom clouds based in space, we in experiments like AGE, etc., which will dramatically make the sensitivities much better. So here is what the so when we overlay the future projections, this is what the parameter space looks like in the same plane, which you can see that so in the gray shades we have the current atomic clocks, and this is what the thorium 229 projections promises, which is really a really great advancement in the sensitivity. And this is where the space-based atom interferometers sit, and these are the upgrades for the crystal oscillators, which are basically the successors of Origa type systems, but in different crystal based systems, which basically measures the mechanical oscillations of the fundamental constants. So these I'll skip over because this is sort of a known story where we have the resonant cavities. So here the only thing I want to focus on is when we start from gluon couplings, as I said, we can readily generate the pseudoscalar axion photon couplings at dimension 5, which is probed by these resonant cavities, haloscopes like in experiments like ADMX and stuff, that you can see here. And also through pion mixing, we can generate all these quadratic interactions as we have talked about so far. So basically, by turning just one coupling, we can generate all these different interactions, and by that we can have a whole parameter space probed by different experiments over almost 25 orders of magnitude, which is a huge feature in this precision sensing. And now, very quickly, we can go over the complementarity with astrocosmo searches, which is not from our work, but the thing is, so this is a very similar work where the authors have looked at quadratic photon couplings with ALPs for a leptophilic ALP scenario, and there we can see that these purple shades are all these clocks, etc., and we have got the complementary limits from BBN, etc., and also we have black hole superradiance limits there, and also the Lyman-alpha, which are basically the typical ultralight fuzzy dark matter bounds coming from cosmology. So basically, the thing is, this is just putting the clock searches into a broad perspective, where we have complementary searches from cosmology and the lab-based searches, which sit very close together in the entire parameter space. And then I'll just end with a very intriguing question that I think is useful to bring up. That so far, if we look at this plot, then we can see a fantastic sensitivity in precision searches. So we can measure up to 10 to the minus 22 GeV inverse for a very small dark matter field. So when it comes to understanding dark matter, it's worth asking whether sensitivity is really the limiting factor, or whether we might be missing something something more fundamental. So, which is to say that a null result in any of these experiments does not necessarily mean the absence of dark matter, but it could also reflect how our theoretical assumptions like symmetries or cancellations or even blind spots or analysis strategies shape the signals we actually look for. So perhaps the real challenge is not just improving sensitivity, which we can see that thanks to all these technologies we are getting better and better every day, but also ensuring that our observables are aligned with the underlying theory. So low energy precision experiments such as LIGO or atomic clocks or resonant cavities, so they typically search for dark matter as narrow peaks in the frequency domain. But however, a single Fourier peak is really not enough to determine the nature of dark matter. So which means that if there is a signal, you will always see the peak. But a peak, just a peak, does not say anything further about what sort of spin structure or the interaction structure dark matter can have. So to break this degeneracy, we need to observe the same signal across complementary observables. For example, we can compare frequency shifts in atomic clocks or electromagnetic response in resonant cavities or even spin precession experiments in NMR type setups. So which is to say that each of these probes should if we can find a system which probes a different coupling of the same underlying field, and then if we combine them, then it might allow us to disentangle the underlying interactions. So in that sense, future experiments should not just act as detectors, but as model discriminators. So then, and this is precisely the idea we are beginning to explore in the context of FLASH, which is an upcoming megahertz haloscope in making, where we plan to target complementary signatures in a new frequency range. So to wrap up, axions and ALPs give us a very well motivated framework for ultralight dark matter. And what's particularly exciting is that we can probe this parameter space using precision tabletop experiments on very realistic timescales. And that really changes the way we think about the problem, because it creates a direct link between fundamental modes of the fundamental models that we have and the low energy observables which we use which we probe using low energy EFTs. And in that sense, the goal is no longer to just detect a signal, but to also actually understand what kind of dark matter we are actually seeing. So I think precision sensing can give us a real handle into looking into this sort of physics more and more in the coming days. So we'll keep our fingers crossed, and thank you all for listening. Thank you.
Yeah.
Thank you, Sreemanti. Fantastic talk.
Thank you.
Are there questions or comments? So just remember the audience that you can ask questions through the chat on the YouTube. I don't see for now any question, but I have some, if you may.
Okay.
So from the very beginning, let me see if I understood correctly. So it's an ALP, right? So in the UV, you start with some pseudoscalar interactions, right? But you say that when you go down to the chiral perturbation theory, you generate some scalar interactions?
Yeah, so by scalar interactions, I meant these sort of, so A square over F square coupling, which is, I mean, not gamma 5 interactions, right? Because...
So not derivative couplings, what do you mean?
So what I mean is, so here at dimension 6, we have all these quadratic couplings, which is not proportional to gamma 5 interactions, because at dimension 5, you can also generate couplings like, say, for example, okay, let me just go into here.
So wait, there for instance, why it's not a derivative coupling for dimension 6?
It doesn't have a derivative coupling because it breaks the shift symmetry. So we have the QCD, which so here we have. So this is how you So this is how you generate the A square over F square interaction. So it's very similar to chiral rotation in that sense, that once you start from gluon. So once you just switch this on, then you will end up with your quark mass matrix looking like this. So this is just normal QCD chiral rotation part. And then when you rotate it to get rid of the gluon phase, then you will have and then expand it in terms of like an expansion in A over F. Then you can have the pion mass breaking and then this shift. So this basically breaks the shift symmetry, and then we can have these scalar-like. So yeah, so basically I meant that, which are not spin-dependent couplings anymore. And this is super important for us because, I mean, unless we have things in this structure, because if we still had a gamma 5 there, then it wouldn't give me a shift in the nucleon mass or the electron mass. So this is absolutely essential to get signal in quantum sensors, like the ones I talked.
I see. Thanks.
Yeah.
Questions?
So before we move on, because I was trying to understand this quadratic interactions too. I mean, do they need to be under the QCD scale? I mean, what scale are these new operators generated? That's what I didn't understand.
Yeah, so this is much less than the pion mass. So here the ALP mass is, so this is basically below QCD, and then you have like very lightweight axions here. And so all these interactions are valid in that scale when we are matching from with the chiral Lagrangian. So the scale is basically less than the pion mass. So that's the scale we're talking about.
I see. Because yeah, I was wondering if this could couple quadratically to the Higgs, but no.
No, then I mean,
Okay.
you will have some interactions, but not these. And then so you will, I mean, what will change? Yeah, so the Wilson coefficients will change a lot, and then yeah, so that's like a completely different regime. So this is not valid in that regime.
Right, that's what I want to know. Thank you.
Good. Further questions? I have more. So
Okay.
when I think it was slide 34 when you show the prospects. What about Lisa?
Yeah, so that's an important thing. So Lisa, so there have been works where people have looked at Lisa, but this is not. So I haven't drawn Lisa here because Lisa sits somewhere here, and this is not as good as this optical clock. So it's sort of it'll probably be somewhere there. But definitely, people have looked at Lisa sensitivities for ultralight dark matter searches. So it works definitely.
Okay, but yeah, so you're saying that LIGO for that purpose is better than Lisa?
Yeah, because
That's surprising.
because LIGO is because of the frequency band, because here we don't really have anything to compete it with. Whereas, I mean, if we go just a little bit below, then you will always have because the optical clocks and the cavities, they are really precise machines, so it's really difficult to beat them. So LIGO fortunately sits just outside that range, so there's practically nothing to beat it with. So that's, I think, LIGO scores better than Lisa at the moment.
I see, thanks. I have another one. I think it was slide 43 when you compared the result with astrophysics and
yes, 43. Did you mean this one? Because that's the only one I think I had. 45 maybe?
No, before.
Okay, because here I don't have any astrocosmos.
No, that one, yes. So this microscope, I think, is like this.
Yes, so that's
what
the
is that?
equivalence principle. So it's sort of it measures the valence of equivalence principle. So it basically a satellite. So where you have like test mass, and then you measure. So it's a sort of a fifth forces limit, but on a satellite, and so it's like a EO wash thing. So they sort of measure the equivalence principle
Okay, but that's an actual
measurements.
bound, not a projection.
No, that's an actual bound.
So that means that most of what you're excluding is already excluded.
Yes, yeah, of course,
Okay.
but I mean, yes, because so what really happens is, okay, but here's an interesting thing that in the CGG, because microscope basically works with nuclear, like hydrophilic, like nuclear, how do you say, in dense in nucleon test masses. So if we have some other, so that's why it's so strong when you're testing gluon couplings. But if we look at the same thing, say, for example, in a leptophilic model, so then we can get rid of, so these microscope bounds will weaken a lot, because so for that, you won't be able to get a good signal from microscope, because we don't, your ALP won't couple to nucleons in that sense. But the clock limits will remain the same, because it will again measure the electron mass shift or fine structure constant, which works pretty well in the for the leptophilic couplings as well. So it really depends on the sort of model you use. But yeah, you're right that when we have a nucleon, we have more nucleons in the theory, then it's really difficult to get rid of this microscope limits.
Okay. Thanks. Do you have further questions or comments? I have a last one. So there's also like a dashed light blue line here.
That's
I
the
think.
QCD axion. So that's the theoretical band from, so it should have been a band, but I mean, that's just the KSVZ line from the QCD axion.
Okay.
This is just to show where it stands. So the clocks are still miles above the QCD axion line in this range.
Okay, and the last question, but then I stop. So I understand the spin zero is the most interesting part because of QCD axion, ALPs, all that. But does it make sense to make us like the equivalent exercise for spin one?
There are actually heloscope limits, so all these experiments work pretty well for dark photons. So I mean, there are a lot of references which talk about that. But for the clocks, I actually don't know of any reference that I've looked at. But yeah, LIGO has been been tested for dark photon models, where people have, so instead of, so for scalars you just have uh, like shifts in the interferometer arm length. But for dark, so when you test dark photons with LIGO, they measure polarization instead. So there have been limits, but the clocks, I don't know why people haven't done clocks. But yeah, I mean, definitely that's doable if you can cook up a theory that can give fundamental constant oscillation in dark photon models. Maybe that's a bit non-trivial to get, and also you have to probably be also worry about the polarization. And I mean, at the moment I don't have any idea off the top of my head how that will work in clocks. So clocks, like, they work better with the scalar sort of thing, which really measures the shift in the frequency, and that's it. But for dark photons, I don't know of any reference at the moment. But yeah, that's an interesting direction that probably it can be interesting.
Okay. I don't see any further questions. So thank you very much, Sreemanti. It was a pleasure to have you here.
Thank you.
And I think we have next webinar will be in 2 weeks time, right? And also be prepared for we have a special, even more special webinar, number 200, coming soon. So keep tuned. So thanks again, and see you in 2 weeks.
Thank you. Bye.
Thank you, guys. Finito. Ah, se nos fue otra vez.